notes until I started to try to make this little spiel that I was going to give at the beginning of the lecture. And then I realized there was way too much to possibly say. But we are incredibly lucky to have him visiting. He's a visiting fellow at I2SS for just a couple days, only a few days.
A month.
A month. But, you know, only a few days. Relative terms. Oh, no. Previously, he was the director of the Tinbergen Institute. So that's apparently named after the first person to win an economics Nobel Prize. So I learned that this morning. And director of the Econometric Institute, professor of econometrics at Erasmus University in Rotterdam. He's a fellow of the International Society of Bayesian Analysis, the co-founder of the EC2 meetings of European econometricians, the co-founder of the European Seminar on Bayesian Econometrics. His publications consist of several books and more than 180 scientific journals and papers. And this was just everything I could fit on the front of one page. So, please take it away. We are so excited to have you.
Sure. Thanks. People always say it's always embarrassing.
But that's my job. I'm supposed to embarrass you.
Thanks very much, Tess. Yeah, maybe to introduce myself. Tinbergen Institute is the joint graduate school of in economics of three universities in the Netherlands, and that is of Erasmus University, which used to be Netherlands School of Economics, the University of Amsterdam, and Free University of Amsterdam. So we have about 180 PhD students. So it's a 5-year contract.
Just remember, we have a microphone somewhere hanging
yes.
around.
Yeah, I got that. I have to.
I'm so sorry. I keep forgetting about. You can keep introducing yourself. I will sort out this cord.
Yes, but I.
Oh, you would like to make sure this is on the record.
No. That's just my favorite introduction.
Now you can clip this on your lapel. I assume this is.
Whatever you want, so it's not important for a while.
I think it's
That's okay.
on. Off. No, on. Good. I'm glad I saw that.
Okay.
Okay.
And how do we know that it's recorded now?
Well, it's got a red light, and
Oh,
the
yeah.
other one is going for the video.
Okay.
So
Good. I don't have to do anything.
No.
Okay.
That's what they tell me.
Okay.
Most of the time it works.
Good. Yeah. As I said, by way of introduction, that was something for us, the way to elevate, let's say, our graduate program. It's well, you're here with your private universities, particularly this one, with a huge endowment. We are all publicly funded universities, and one of the things, it's 1987, so when I was a young faculty member, that they started to have this joint graduate school. And so because joint research, it's also a joint research institute. To be honest, that doesn't work so well because faculty is still in their own place. But the joint graduate school, to have a tough, we have a rather selective program, and that is a phenomena that you see more and more, I can tell you, in Europe. Because we are all publicly funded universities, except a few ones. And so Cambridge University, I've been there for a while, so I know that Oxford, LSE, they're kind of privileged that they have enough money. But the Barcelona Graduate School is also something joint. Paris has now the so-called Paris Graduate School of Economics. It's also a joint of 3 or 4 universities. Then you have to be elected based on the number of publications to become a fellow, and then you can teach in the graduate school. That is a bit what I did. Now, so on what this thing. So here it works, and there it doesn't. Yes. No, this is your particular screen, but I can. So the technical title of what the title of my talk here is very technical, but I'll try to do it much more intuitive. The topics, what I would like to talk about is the forecasting with different models and different sources of information, which is something that we like. In economics, we have very often governments have several models. They have a forecast from an annual model, a quarterly model, a sectoral model, and how do you combine? How do you deal with that? And very often, that's one reason. I wrote down my intuition here. Another point is that, as I said, I am a Bayesian econometrician, which means that we don't believe that there's one true model. So there's different models which may be useful at different periods of time. There are also different sources of information. A topic that I very much like nowadays is use expectation information, just opinions, combine it, and that's what I will later do. It's survey of professional forecasters. Can we combine forecast density with a model density? And so there's a forecast combination idea. Then, of course, is how do I do that forecasting? That's a bit of a technical thing. I will do it with a weighted average, and I will have these weights time varying. So a particular model is used in a particular period of time. How do I update these weights? Sorry, it's through a particle filter mechanism. So it's like a Kalman filter. If I have many models, it's very computer intensive. So since a while, I discovered parallelization, and I'll do parallelized computation. But I'll do it all. But in order, and I do this with my Italian mafia. So this is a PhD student of mine, and he's now at the Norwegian Central Bank. And it's very nice because he came from University of Venice. So, and that's what I can recommend. Get a co-author at the University of Venice. And indeed, once in a while, my wife and I go to Venice. And he is, and he was in Denmark at Create. He is now, Stefano is now in England. Okay, so, but this is what you would call with a dinner an amuse. So I first thought to introduce a little bit what I do. So this is I'm working, it's a bit a hobby because I'm very much more a technical person, but I've been asked to write a paper on the history of Bayesian econometrics. Now, this is when you can use so-called connectivity analysis, visualization techniques. There's a connection of keywords of Bayesian papers in leading econometric journals. So about 1,200, and you do how you can use these visualization techniques or keywords, and you do a combination. So when you see Bayesian analysis, it's very related to forecasting. So if this is a cloud here, model uncertainty forecast. So this would take another 20 minutes, so I'll do it quickly. But so variable selection, this topic in econometric co-integration, which is one of my hobbies. But so forecasting, then here in time-varying parameters, state space models. And I talked about particle filters. It's like Kalman. It's more a generalization of a Kalman or normal filter. So that and option price. It's very popular in finance. It's also here panel data, Gibbs sampling, of course. Those of you who know numerical analysis, Gibbs saved Bayes in the sense Bayesian analysis was very tough. And Gibbs sampling and MCMC. Importance sampling, this is what I did in 78. It's my PhD, and so really an interest. And still done. So panel data, and this is a bit in marketing, the choice models, where you have a lot of individual data, diffusion models, there's hierarchical Bayes, etc. So just to show you that, so in my world, in Bayes, sure.
What exactly is what's space and color in this?
Sorry?
What's like space and color in the
this means that it is that the more keywords are here in what would you call it? Purple? I'm very poor at colors. Blue, purple, etc. And the lighter. It's the whole idea to say this is where all these keywords gave an important indication here, and so these are in a sense topics that these. I have 10 journals and 1,200 papers from 1978 till 2012. Of course, I have a good PhD student who did that.
The keywords are the ones that the authors
Yes. So it's certainly it's not a random sample. It's experts, kind of experts' knowledge. Huh? And I can tell you how I came across this. Is that I have a colleague in operations research, and on his door was a picture like this. And he said, "Oh, it's a simple algorithm, and you can just pull it in. And if you have a clever PhD student, he or she can do it." And so it's not. This is kind of you minimize a distance between these words, etc. Anyway, this is the second thing, because that's more. You connect the topics and the authors. Now this is very difficult to read, I see, and so I would have to go back and then enlarge it. I'm not very good at that, so please. And anyway, it would take a lot of time. Again, the dark blue areas. Yeah, you cannot see anything here. MCMC. If you, I can see it here, and I know it. This is my name, Van Dijk. But Arnold Zellner is here, of course, a very famous Bayesian. John Gaywicker, a statistician and a very good friend of mine. So there are quite a few. Neil Shepard, who just, as a catch, he went from Oxford to Harvard Economics, and he's not quite a Bayesian, it's a bit but this is again the key area, MCMC, Markov chain, Monte Carlo, in a sense numerical methods again save Bayes. So so it looks a bit like I said, map of the United States, but it's not. It's really again so a hot red area. This field of marketing and the names. So when you would be in the field, you would really say, now I want to know, am I listed there or am I not listed there? Okay, so this so let me now go back to the serious kind of things. What I want to talk about is the motivation why suddenly parallelization is becoming so important. The reason I come very often to Boston is also personal. I have a son who is in neuroimaging. He's at Harvard in the Brain Image Center, and they live around 7 years here. And they do also. I never expected that I would have a son going to science, but when you just want to compute the correlation coefficient between what happens here and here, that's what they do. Very descriptive. The 5 billion neurons, and they have an enormous amount of computation. They already are far ahead of economics or social sciences. He has one line of extra code and then 125 computers just compute that correlation coefficient. So the parallelization since 2 years, it's more important. So I'll talk a bit why we do parallelization. Then the idea of a combination scheme, because the combination scheme is by itself, is what someone said in the audience once. So this is the first time, but still new, and I still do a lot of work here. Is that the combination scheme itself is not all Bayesian. I can apply it, someone said. To make that scheme dynamic, for those of you who've worked a bit with state space or dynamic, it's a time-varying parameter model. It's a time-varying, and I will use that idea. Then I'll talk a bit about parallelization. I do a bit experiments with simulated and real data, and I probably do a financial case study where it's the battle between survey forecast and model forecast, and my advice is do a combination. So it's a line of research that I'm still following very much. So this work is now, central banks are doing it. Central bank in Norway, but that's where my PhD student, they have 200 models. They want to combine that in some clever way. We're presently working on 120 US series, where we say we have 128 models, and we combine them. And how do you do that? And how can you do that mechanical or intuitive? It's also, we have, if some of you do factor models, where you're not sure, and we have a factor model where we do the number of factors to forecast a business cycle, and we do We don't do forecasting, but we do nowcasting. That is, nowcasting is when observations come available now, and they are revised and revised again, and that affects forecasting, and we do their kind of weighting. Okay, so first on this parallelization. So until 2000, roughly, the increase in CPU was strongly related to increases in megahertz. And well, these are technical things. That the memory wall was an issue, a power wall, a temperature wall. But this is the picture, roughly. So from 1970, and this is CPU speed. But the whole idea is that you have this line, this constant line that from, I don't care so much, but in the period, I can tell you this roughly where I started. And so I still, I don't know, several of you must have done that too. Of course, I still worked with a deck of cards. Then we had, I also worked on a 386. Then slowly came the desktops. And of course now I have my MacBook Air and the Pentiums. So, but it went up, the kind of, you could almost say a kind of constant increase. But it's slowed down and it averaged off around, well, 2000 and later. So the story is that the evolution of the CPU performance, that we can do again and again, the free lunch is over. And I can even do it more dramatic, that my former supervisor did least squares, and there's a famous estimation method, so-called two-stage least squares, or instrumental variables. Harvard Economics has done that, and my institute did that, two-stage least square. My former supervisor, who started in '56, he said we had to do a 5x5 inversion, and we had to do that, and we had a big paper. It took us a whole afternoon to do that 5x5 inversion, and so you better not make an error, and then finally you got to the so-called two-stage least squares. Now in a millisecond we can do that. So the issue why I'm also interested in parallelization is the more we can do, we can solve problems that we couldn't do. I have now a 70 times increase in speed. So we have certain computations which take a week, and we can now do it in half a day. I was last year at Harvard Economics. There was someone who had data from 1850 till 2013 and predicting tensions, so war tensions, and he did a Bayesian so-called MCMC algorithm. And I asked him, well, how much time does it take for you to do these computations? 3 weeks. I thought, oh God, this is really terrible. And I said, can you do it sequential? Sequential would be, take 2 years. So these are silly things, and that take so much time. You have to think about it. Now, the evolution of from a CPU to a graphical processing unit. I don't know how many of you are interested, but these are these cards. So there are several ways to do parallelization. One is to have many machines. That's what I learned from my son. They had 125 machines where you can just send a thing. It's like if you have a matrix vector product or an inner product. You don't have a whiteboard. Yes, that's what I know, but where can I?
Yep, right there.
Yeah?
Anywhere. So that happens if you have a private.
Sure. Yes. See, we had a thing like that, but then it was a wall, and it was not too good. Someone did that. So x is, let's say, n by 1, y is n by 1, and you want to do sum xi, yi, I is 1 to n. When you can do each of these multiplications, you send to one machine, so you can do it so much quicker. Then that's the simplest type of parallelization. You see that, but there are But the issue was, and I learned that the video game industry, they were ahead of all of us because they are the ones that did this advanced computation and the parallelization and the GPU cards. These GPU cards are released every 2 years, apparently. So you can see this in my co-authors who do this much more than I do. I know the intuition, but not the uniprocessor speed is not doubling, and the GPUs are the alternative. And the picture, and this is really, I got these pictures somewhere, and I asked them, explain it to me. So when you see from the core, from dual core, quad core to multi-core, this is the CPU time. But when you have these GPUs, you can really go to, how we do now, 512 or 1,000 core computing. And that really allows you to solve problems that we couldn't do before. And that is really, so that's also why I have my story where you did with the cash register in the 1950s and so I do think, it's also what I told my younger deans, get these persons GPU cards, because then they say, oh, it's $300, and then our budget is not for that, etc. It's totally silly. Anyway, so, okay, so, and the path to performance is either a fast processor, the CPU, and most of you have quad core, I guess. And, so we do both CPU and GPU, and multi-core, anyway. So this, and that you can do it in a single and double precision. This also is also for like the older people like me. I did things still 20 years in single precision, and then it went double precision. And when you do a lot of computation, a lot of additions, yeah, very careful. But so let's not. Okay, so this is my story about parallelization, and now we get to the more intrinsic parts. So the density forecasts. This is also what I like much more. It's not just a point forecast, but the complete distribution, the density of complete distribution. That's becoming so much more interesting. Why? Because of the crisis. We want extreme events. We want that probability of both you have stress tests. What's the probability of negative growth? What's the probability that the US will be in a slump? A slump is poor growth, high. You have here you have what people call, was a very interesting paper somewhere, the jobless recovery. You have a kind of recovery in this country. It's similar in European Union. So finance, other sectors do recover, but not really the unemployment. Why that is, that's kind of interesting. And what you would like is to know what's the probability of these things. Now in finance, the asset allocations, higher moments, of course we have the Markowitz mean variance, but also for those of you who work in strategies, minimax strategy or maximum strategy, extreme strategies. And this is why central banks, the software or the paper that I'm talking about is just on the revision, the Journal of Statistical Software, and it's a very popular journal, I discovered. And the software is now used, so it is not a topic, it's a bit technical, it's a topic. The Norwegian bank, the Polish bank, I got a note that they want to use it. In Chile, the Bank of Chile, and in September I go to Portugal, because the Portuguese central bank wants also to learn about these things. And the software is really available. It's in MATLAB. Anyway, so why? I think averaging is a tool to improve forecast accuracy. This is a very famous Baton Granger paper. And and the other ones. So, but let me only sketch you. So averaging is interesting. On the other hand, there's model uncertainty. The model performance may vary over time. The model set may be incomplete, which is something very difficult for Bayesians. There may be correlation between forecasts, and models may perform differently. So maybe specific weights, and let's So what I did with Sue and another Monica Billio, she's also at Venice. She is a female full professor there. We did a stage-based representation, and yeah, I guess for this audience not that interesting to do these technical. Let me go to my examples, and that might be more interesting.
Can I ask
Sure.
Sure. So, and this is not particular to the topic, it's just something I never quite wrapped my head around. Like, what is the nature of the penalization that we would put in place for adding an additional model that we're then sort of throwing into the combination, right? Okay?
I will get to that. What the penalization would be that if it has poor forecasting possibly in the past. So this is so I will and then we'll get back to because this to the let's say flesh of the paper. So what we do, we want to do some time varying, we want to do some learning, etc. So let me even skip this because there's linear pooling. Yeah, what is a combination scheme? And then I will get to the example, and that helps much more. So the whole idea, say, it's very similar to, so I have a density of the observed variable given all the past, y1 double t minus 1 means all the past, and that is the marginal of this joint density, and the joint density is the combination of the observed given all these are the predicted values. So it's really this whole idea of f of y is the integral of f of yx, the x, and I can do this as the conditional of y given x times the marginal x. And so this is all very standard. So I have predicted values. The intuition is I have some models, and there's quite a few here that have predicted values. So this is a vector, and I'll get to specifics later. The intuition. And so I have predicted values, and I want to combine them in a kind of formal way. Now, how do I do that? Is to say, okay, I have a weight function, which I plug in here. So I'm talking now about the f of y w x, and I can do that. So f of y w, all the past predicted, and I can decompose that in given the weights, the density function of the weights given all these predicted times the predicted values. So the intuition is I simulate values, or I have predicted values from each of these models. I combine these with predicted values of the weights, and the story is, of course, how do I do that? For those in statistics, what I do is a convolution, and I do it numerical. So it's a numerical way of convolution. It's a bit what I want, because I want to do it rather complicated, and that is the more restrictions I add, the more complicated this so-called combination. A simple convolution. You learned that a convolution of normal densities gives a normal density. Convolution of gamma density, of Poisson density. It's closed under operations. And that's what not. So I'm going to allow all this to do numerical. The price is that I do heavy computations. So I want to allow for an incomplete set of models. I want to do averaging. I want to have these weights random and learning, and I want to account for correlation. So let me do that now specifically. So now we get to what I really do. And so I have here, and I wrote that down, otherwise, because I went a bit too quick on, I think, as my example. That I show it to you. Can you also read? Yep, yep.
I just wanted to ask a quick question, which was, can you just give me a couple examples of what kind of quantities you'd be
Sure,
using
sure.
here? Just not being an economist, I don't know what
No,
to
no, no.
imagine.
No, so y tilde t are the predictions from, because that is what I should say to you. So I skipped a few things. That is a k L by 1 vector. So I have k models and L variables to be forecasted. So I have, and I stack them in a long vector. So, and suppose, this is my example, suppose that k is 20, and L, so 20 models, and I want 10 variables. So then, right away, I have here 20, so W is an L by KL, because of what's important, matrix for each T. So I already have here, it's 200 weights, and that is what has a computational complexity. Okay, so it's in a sense very intuitive. I have all these predicted values. I want to combine them, and in a sense, this is my combination scheme. You can see it's a normal density that I took as a combination scheme, where the correlation between these weights is the sigma matrix. The sigma gets very high. Now, I want to have a probabilistic interpretation of these weights, because I talked before that I had a probability distribution of the weights. So these, and it's a discrete. So these are logistic transformations of some unobserved latent process xt, and it's a logit transformation. And that is the technical, and the model that I'm going to use. Then I go back. So this is my model on how these latent weights, and this is what economists would understand. So the density of the weights, and what kind of model is behind here? Well, it is that xt is xt minus 1 minus delta et plus a disturbance, eta t. And because that is what is listed here. Delta xt is xt minus 1 plus this. So I really think, and what is my et? The et is a sum, this kind of a so-called moving average. It's a sum of forecast errors of the past. So and I go from 1 to tau. So it can be 6 periods, while we took 5 to 6 periods. It's a kind of it's a moving average. So what you see is that this latent weight is like a random walk. That's the previous value minus a disturbance. So if in the past you made a substantial forecast error, that particular model, then the weight is less. And so in terms of the literature, it's so that's Debo, Frank Debo, is 10, and they did already an old idea of time-varying weight, and I've also done work on time-varying weight. The whole idea of time-varying weights is what we very often did with time-varying parameter models, where you say the basic regression model. Again, so if you think you have y as x beta is u, the simple regression model, very often people say, no, beta is beta t, and beta t is beta t minus 1 plus beta t, the coefficients. And the simplest would be to say that y is a constant, mu as constant, but this mu thing is moving over time like a random walk. And this is, well, then how to do this in the normal world is what the Kalman filter does, and Kalman updating. And time-varying patterns and structural breaks, time-varying patterns, it's a very hot topic in economics. We say we don't have fixed structures anymore, we have time-varying structures. Now that idea here, that is what I transferred to models. I say I have particular models with particular periods where I take the prediction. I have many models, several models, and I take their predictions and I weight their predictions according to their performance in the past, so there's a lot of error, we get a lower weight, and because I want to be probabilistic, so as I start the beginning, I want to combine these, that my forecast density is a combination of the densities of each of the models, and I'm completely probabilistic, and for the more formal persons, I do not violate the likelihood principle. I'm a Bayesian, and there are other very work by what's called other authors. Kewakan Anisan is very good friend. He's a very famous Bayesian, but he is not in the strict world. Yeah.
So you're using the weights are being estimated by their performance of the model in the past.
Yes.
Why wouldn't one sort of like make use of what you might call future information and say,
yep.
like, go halfway in your time series and calculate weights based on out-of-sample performance of the model into the future?
There are certainly other possibilities, yes. So, as I said, this is a combination scheme, and there are certainly other things that we presently have, like in brainstorming, what should we use expectations? That's kind of what you would...
Well, it's like, I'm going to evaluate the model based upon its sort of out-of-sample performance. I'm going to weight the importance of the model based on its out-of-sample performance. And by out-of-sample, I'm meaning, like, take your time series, split it in half, and choose the second part of your time series as the quote out-of-sample. And I'm defining my weights based on that rather than looking back and seeing
only, Well, it would, it's certainly interesting, but it would create other ways to for calculations. But it's, there are lots of possibilities here. So the particular analogy that people did in finance, this is like a portfolio analysis. I have a portfolio, I have a set of assets, and I rebalance my portfolio every period. People in finance, a guy in finance saw it, and he's still going to send me in a few months or so a paper that he said, I can exactly use this combination scheme in finance. So I rebalance always my portfolio. How well did you do in the past? What kind of profits did I make in the past? And I rebalance. And he says, I do not even want these weights to be contained to the unit interval. I want to kick out a particular asset. So I said, why don't you do that? Why don't you have a set of models? One of the models does so poorly, you kick it out. That again is something have to be difficult. If I'm also trying to be a bit formal, which is behind here, I don't know, a transformation from a larger space to a reduced space, and from a reduced, if I add things, that's also.
Are there other examples other than finance where this gets used? I'm just trying to put it all together with things that I might have.
Well, person said in.
You're saying that all these banks are now, like the Norwegian Central Bank, and what type of outcomes? Are they interest rates? Is that like
they use it for very much for GDP growth and inflation. and so what kind of growth. But they really have quite a lot of models, and in I would say in political science, someone said if you have very controversial theories, in economics you have the Keynesian theory and monetarist theory. There's someone in Penn now who does a little bit, uses part of this, and he said, I look at a model which can do the financial sector and a model without that financial sector. And how can I see the crises and the frictions, if there's a model with frictions, and can that have a particular weight? It's Frank Shortide and Marco Del Negro. He's at the New York Fed. And, okay, so, and certainly, someone said, the technical, this is a norm, an L2 norm, and they said, can you do so-called, it's a little bit related to what you said, predictive likelihood. Can you not do a kind of predictive analysis? And so, of course, I will remember it, because this is what I assign them to you graduate students, and say, experiment. There's not a theorem here. So, okay, so how do we now do that? And this is one slide, and then I'll not do too much technical analysis. So, what I started intuitively before is that I have this conditional density of distribution with density function this, and how do I approximate that? Well, I draw, and now it gets also to computational complexity. I draw m independent values from what should be right here, from these predicted predictive densities, and conditional. And now life gets difficult, so I take a big jump. So I said I have to do these weights, and I did not tell you. And I thought not to skip that. But say, how do you do that? That weighting, these W. There we use so-called particle filters. And for those, we take a Liu West, a regularized particle filter. It's in JASA, but it's rather what I learned. It's very mechanical. It's like you take a particular weighted average. It could be arithmetic. It's a bit. And it's very it's what people thought of. How do you have these? You weight that. You on the one hand, you have unknown parameters, and you can estimate it with your favorite. We would do it the Bayesian way, but you can do that. And these weights, the notation is always called. So then, given this combination of these weights, you can simulate values of your predicted density, and then you take the weighted sum of all these predicted values, and these are the weights, and this is the Dirac measure for more formal analysis. But the intuition is very roughly that it is, as I said before, if I have the f, x, y, the x, so it is something, and so this is f of y, and I said I can do that as the conditional of y given x, f the marginal of x, dx, and what you can do, I simulate from this marginal this, so I simulate x values here, I plug them in here in this function, then I take an average, and that's what I get. So, to a certain extent, the technique, the price, of course, is that we do this dynamic, and there is some hidden complexity. And but again, the intuition is that because there are lots of computations, can we do that with a GPU? And it's very easy in MATLAB. And there are so-called NVIDIA cards, and we are able to reduce computation up to 70 times. But this, there's a lot of times that some people say 1,000 times. It's a bit unfair because it is always, so what do? Do I have, and this is what we did. We had the fast machine in Norway with parallelization and a fast CPU, with a poor Roberto Casarin in Venice with a 10-year-old old machine. So these, I exaggerate a bit, but I've seen statements in the statistical literature where they have say, oh, we have a speed up factor of 1,000 or 5,000. Of course, it depends. Do you do Champions League with minor divisions? And that's, now, what is the computational complexity? And then I'll go through it. So I have m. So it's m, the number of draws predicted, n the number of particles, these weights which come from some mysterious way, from the length of the time series, the number of predicted densities, and L. So here I took k as 6 in our empirical example, but we'll do it even simpler. So there's an enormous amount, 1,000 times 1,000, and then k, L, where I had 20 and 10. We really work now with 120 and 10. So okay, and here also I will go quickly. What you can do, and as I said before, what is the easiest in parallelization? As soon as you have the inner product or a matrix product, then you can, as you already know, you do piece element by element, and that's what you can send. That's also now similar is what we do. So then you can make a matrix, and so you have to believe me. So we do this, and there's a simulation algorithm. What I would want to do and to explain a bit is okay. Suppose so it's our models are not as behavioral as most of your models. So this is a regular time series. So we take M1. It's autoregressive. It's a bit an issue in the economic literature that very much a random walk model is the best forecast for tomorrow, today, or is there a memory? Is there autoregression? And the world is terrible on the number of tests, whether there's a random walk or not a random walk, and can we beat that random walk? And part of my work has been to say, well, I don't know, it's 60% random walk, 40% stationarity, and let's take a combination, and let's take a linear combination, and that is to a certain extent what part of this work, what motivated me, and so this is almost so-called light white noise. This is a bit stationary and in between. Now, what we'll do is the following experiment. Sorry. So M1 is the true model where we simulate the data from. So an M1, you have to think what is a forecast, an unbiased forecast. That is it is 0.6 over 1 minus 0.9. So shows that. So we're very interested in the expected value of the y1 given all the data, and that is really it is the constant term. So in equilibrium they will be equal, and that's what you always do. You say 0.1 over 1 minus 0.6. So and it should be 0.25. Oh. 1/4. And the other ones, so what I do, so the whole issue is it worthwhile to combine models if someone's not correct? So here the unconditional mean is 3.375.56. And we'll do another experiment where we say we simulate from the true model, but we don't have that true model in our data set, so we just have M2 and M3. But both, that's how they are constructed, both are unbiased, they have an unbiased mean. That's similar to, and how are the results? Now, if I have biased predictors, and I have my learning, so these weights, and this is over particular periods. What you see, and this is the mean of these weights, and this is a confidence band. So after 40 periods, if I have a true model in it, and you have bias predictors, you see that our procedures lead to getting the true model a large weight, and all these go to zero. But what surprised me is that if I have an unbiased predictor, so the M2 and M3 were unbiased, but they're not the true model, then it's very interesting that they still get a substantial, well, M2 get a good weight and this get a good weight. So the method selects the true model possible, but as soon as if I have models, although they come from a different source, but they give has a mean forecast, it's not too bad, then it's worthwhile to keep these. Similar, if I have now an incomplete model set, so I simulate it from the first model, but it's not in my data set, then the model which is closest to the right model gets a lot of weight and the other zero. However, when these models give me reasonable, so-called unbiased predictions, then the two models are there. And that was kind of very learning, and we can break switches in the paper. So what we now, one more experiment, and then we do the combination method for different degrees of learning. So what we do here is M1 is the true model, and we let this phi vary between 0 and 1. And then I have to look up again when at particular values. Oh, I forgot that now, top of my head. So when, oops, oh, I didn't write that down. When phi is a particular value, 0.6 or here 0.8, then M1 and M3 are okay. Now, these are so-called heat maps. That is the weights. When they're black, there's zero weight. Now, if I don't take this learning into account, then clearly this was this first experiment where I had biased predictors, and it's all black. It's only in the beginning and only here when this phi is such that model 2 closely resembles model 1, then the second model takes, and otherwise not. But so here you still have that the other models get a particular weight, and low and black here also low weight. As soon as I introduce that learning, that past learning, then after 20 periods, the right model gets all the weights and all the models. So a learning, which is computationally expensive, but it's doable, is very interesting. And so for what kind of learning, whether we do predictive learning or other type of learning, it really helps us in doing a combination scheme. Okay, now this whole thing that GPU, CPU, I think you probably believe that, but not really. And I have an application, but I think it's more interesting to go to this case study. And that's, well, of course, unless you have, but you have already that suggestion, which is now in my head, to say, can we not do things on a different way on the learning procedure?
It might be a bad suggestion.
No, but there are several other suggestions.
When the Bank of Norway crashes.
Yeah, exactly.
But the idea is, and of course, so the paper, which is a bit in technical journal of econometrics, we really have experts' opinions learning, and that's why I want to talk about that now. So there are really different. And that is what you would maybe do, and I work with that now in a different context. The macroeconomic information is usually very weak, but we have expectations data, you have opinion polls data, and more we use these. And so what we do here is to say, okay, we have the famous thing in finance, Standard & Poor's 500, the index, and so we have an individual forecast density. One is that we take white noise on the return, and white noise on the return. A return is a change. So the change is just white noise. That means that the level is a random walk. Because this with prices, this delta PT is like noise, then clearly PT is PT minus. So this is the famous idea in finance. Okay, so at the one hand we have that as model, and we have the survey of professional forecasts. And there is and the 40 or 50 persons who every half year give a forecast, and then you can use a so-called ensemble methodology from Slaughter, and we make a predictive density there. The Littleton survey sample is 91 to 209, so we have the crisis, the Lehman Brothers crisis in there, and we do point and density forecast, and we do time period weight combination with learning. And we assume this again. I know I skipped several things, but we think that we take an experiment where we have a investor which has a so-called power utility function, and he has an annualized portfolio return, annualized and liquidation, etc. And he looks at that. Now, so this is already the major thing. So we show outside the red is the annualized return. And you see this is the 2008 crisis. Here is, and here is also the early the dot-com crisis, price here is advanced, etc. Now our mean, somewhere here, combination mean, what you see, the white noise model at this kind of 95% probability interval as the survey of professional forecasters had this one, the small one. These guys here follow because that issues, and you see they miss here a downturn, here a downturn, and they miss terrible this downturn. Professional forecasters usually stick to a mean, and this is kind of interesting to learn. It's also in the government analysis, and that is why if you would follow these professional forecasts, you would be badly hit in investment. Now, our ensemble, our combination tells us that this should be the confidence band, and so we really are doing here. So this is the picture. So in terms of accuracy in so-called forecast evaluation, then the density combination, this is a root mean square prediction error. You could see, in terms of forecasting, it's very difficult to beat these models, these also mechanical models, formulas in finance literature. This is so-called, this is what's called log score, it's a sign, etc. So in statistical accuracy, we're roughly the same. But if we do an economic analysis, then this is a risk aversion parameter. So let's take a large risk aversion parameter, these columns, and then the mean return of the professional survey forecasters would be pretty good. Looks like it would have a much larger standard deviation than the other ones, and this is the Sharpe ratio for those of you who look at that, and then we do better. But in terms of loss of utility, and so large negative is not too good. Then we do much better, and we traced it through time, and then you really see that these professional forecasters, because they over this long period, they missed twice a substantial downturn, and that is what kills them, and where we did. And these are the technical things. So here we would say our model combination does work, and it's really a very difficult type of exercise, because in terms of regular forecast you can't do that much. Now the weight dynamics, it's also otherwise I get. It's still that the white noise is changing over time, but not substantially. The survey forecast is increasing over time, and this is my things which I really like. This is what the model weights, that just to show you a picture, that these model weights differ over quantiles in time. And so this is the survey forecasters, and so it's 92 and 97, and only to say, so if it's a large weight, it's red and hot, and blue cold is a light weight. You just see it is, so this is a distribution, what you have to think, and that distribution is very non-regular. So if it would be a normal density, then it would be very smooth, it would be like bell-shaped. And here, so over time, just to show really that over time it changed very much. And we have one more example, that is how do these weights change in month 6 in 2008, so before the crash of Lehman Brothers, and this is month 12. And you have to think of, because this was a bit difficult, that the range is much larger, twice as much as here, and here also it has shifted tremendously, and what was, so I cannot make much sense, not much regular pattern out of this. I can only see it shifted tremendously, so it's over time that these weights change quite a bit, and that's where our learning comes from. Okay, so
you said they were
sure.
also over quantiles. Can you see that? So is that just the fact that it doesn't look at all normal? It's all wiggly?
Yeah.
Okay.
But it's but clearly someone. When I first saw it, I thought we should let a smoother go over this and make a smoother, and because but yeah. My co-authors who made the picture thought it was fantastic, but they didn't want to do the smoothing.
It was great. You could put it.
Yes.
So what I see, I just want to see if I've understood correctly. So the fact that you get so much more darkness, you have those like 0.8 and 0.9s compared to before. That means that it's kicking out more of the
Well,
or the weight.
it gives what it shows here, because the range is wider, it gives much more weight to extremes.
Okay.
So here it was in the middle of the distribution, and it was still asymmetric. So I didn't tell you even what the axes are, but the idea is a pattern. So it's a bit asymmetric because it's there's still weights here, not there. But that really shifted quite a bit from 15 above 15. And suddenly there are enormous weights here. So suddenly they say, oh, you have to be very careful what happens in the tail of the distribution.
Okay.
And that I should have explained that. But that's the only thing is, someone said, can you do that? This is one particular period, and so if you would do that for all your 300 observations, you would be dead. So interpretation, learning, and that's still because so just to say in summary, so what we do, a combination approach, where like your as I started, convolution of normals is again normal. A convolution of this here, not and the way we do the combination is that we have all these weights time varying, and we do these filtering, and we do a forecast combination. We do I skipped the GDP, etc. But I did the finance. What we see is that with learning, it does outperform middle, and I didn't explicitly indicate that, but it clearly outperforms what's called Bayesian model averaging with fixed weights. I have several papers because it's a hobby of mine. Model averaging with fixed weights, this time varying weights. What we are doing now, and this is, I have another line of research, but this becomes more and more a hobby, is do it with a large model, a very large. The title of the talk was that's again it's a technical, because you have to do a hierarchical structure. You have to make these models, and can we do a much better simulation? We do basically number crunching because you have strands of it's really like this xi yi a combination, and you let the computer do it. You could say, if I know something about these forecasts, then why can I not do these weights in from a clear known density? If it will be a Kalman filter, Kalman is an analytical formula to update. If I could use the Kalman filter, then computations would be tremendously increased. It's because we do everything numerical, and there's one way to do that. And clearly the question would be here, is it at all useful for models that you do, let's say, for a particular government policy or in the social sciences? I once talked to a sociologist on social mobility. Said there's models, cultural models, where there's more chance of social mobility if you're regular middle class. The movement is always in the middle. It's also in economics. It's not when you're very rich, you stay very rich. When you're very poor, very poor. The probability of change is always, we know that. I also know that. I did some work in countries, movability of countries, and whether you could say it's useful, I don't know. It's but it's challenging.
If you're going to open it, well, I'll start asking questions. Thank you so much, though. Thanks so much for coming.
Good. Yeah.
But a quick question I have,
Sure.
you mentioned a hierarchical structure. A lot of this was reminding me of this just me trying to put it into context with things I know, is sort of multi-level modeling and hierarchical linear modeling.
Yes.
And it seems very similar. It seems like what you're sort of doing is doing multi-level modeling with learning.
Yeah. exactly.
Okay, good.
The kind
Then
of,
I understood
no,
most of
it's exactly. And that hierarchical linear model is where you have a lot of analytical results. And I give up on the analytical results. So I went, let's say, completely overboard because much of my other work is much more learning, using model structures. And what is what we see now, we have now experiments which take 2 or 3 days. And then I find it far too long, really. But I find overnight is still good, I think, and then yeah. Of course, when the computers get faster, then I can again say what you can do in 2 days, you can do it then. But things take 3 or 4 days. But it's more and more people just show a result and they say, oh, it took a few days. And sure.
I think demographers look at some of that.
Mm-hmm.
All kinds of models that they go place over time.
Sure. Yeah.
And then, fun book, I don't know if you know it. It's sort of pathetic to you. It's still expert judgment. Obviously, what you do.
No, it's exactly, and we have expert's opinion combination as in as
You know his book.
yeah, I well, no is a bit too much, but I know about
basic result
sure.
Is
sure.
The experts who have one model
Yeah.
do a lot worse than
Yeah.
he calls the foxes,
Yeah.
who sort of have multiple models in
Yeah.
advance.
Yeah. Yeah. Yeah.
That's obviously
Yes.
They're Bayesian model averages.
Yes.
Yeah.
Yeah. Yeah. There is a bit of an issue that, and this is also why I said we need learning. I think there's a famous story about the weight of an elephant, and many people give that weight of an elephant, and there's this small boy that says its weight is like mouse. That's it, and of course that gives a crazy average, and of course then you should do robustness. So this is also what people say. Should you kick out a model? And this is what I say. Our learning procedures should do that, because otherwise, with fixed weights, I also have colleagues who are very against the idea that there are many foxes and that model averaging is useful. They say when you have one rotten apple in a basket, how do you find it? Oh, this learning procedure, and according to Bayesians, if a priori you put a bad model in it, the likelihood to penalize that model. But this is why this dynamics that should deal with it, and that's why I so much emphasize that it took 40 periods for these weights to adjust. So that again, you could say that is because your penalty function, if you would use another more extreme penalty function, it's a lot of experiments. I would say it's not so much.
So are there good examples where, likelihood or out of sample prediction or something really terribly fails to get rid of that apple? I can understand the anxiety.
Yeah, well, good out of sample performance should get rid of a bad apple. But there are also very stubborn people who say we stick to our convictions.
But they don't have sort of here's the example.
That's
model averages and just show you how wrong you are.
Yeah, and see, I did it here, so this is a bit my limitation that I don't do it yet with economic, but I'll go next week or so because I know quite a few people at Princeton, and they are very keen on different model theories. Chris Sims is a very good econometrician, also economist, and they really say that the whole debate about fiscal policy or monetary policy, which of these is effective? And that's what you also, he told me, that is what you should do. So give weight to particular policy combinations, and then say, well, because we learned that policy is not, so your combination scheme, he said, these intuitions and these techniques can be transplanted. So someone in finance said, I'll do it with portfolio analysis. Someone they said, you're still very technical. You should do it intrinsically, more behavioral, for behavioral models, and then say, you get much more dramatic results. Well, I would say, good, but for other people